Okay, this is Professor Jimenez, and this is the second part of the A to D converter lecture, and now we will write the code. So in the first part of this video, we saw how to connect this PIC 16F1619 with an analog input, and we will the PIC will convert this voltage reading into a binary reading, voltage reading, and it'll be transferred on port C from RC0 to RC7, where RC0 is the least significant bit and RC7 the most significant bit. And we will use RA4 and RA5 from port A, from this port, for 10 bits configuration. But we will first do the code for 8 bits, and we will see the extra 2 bits to make it a 10-bit AD converter or 10-bit binary voltmeter. Okay, let's proceed with the code. First, the resolution. We have to determine the resolution of the least significant bit, this RC0 in this case. The formula for that is this. The resolution of the least significant bit is given by the voltage range divided by 2 to the n to the minus 1. And this is the voltage range in this case will be 5 volts. And if we use, and n is a number of bits, so if we use 8 bits, that will be 2 to the 8 minus 1, or equal to 55. So the instruction that we will use to operate this voltmeter using the A to D converter is this: ADC in channel, variable. So this instruction in PVP3 code, right here you select the channel, which can be channel 0, 1, 2, 3, and so on. And the voltage that you read here, the analog voltage, will be stored in this variable. This variable can be an 8 byte, a variable byte, or a word variable. Okay, where a byte variable will only be able to handle 8 bits, and the word variable will be able to handle 10 bits. So the instruction to do this operation is this. Let me hide the screen a bit. So right here we have the first we declare V1 as a variable byte. Then we set up here the label RPT for repeat, and then we start with the first instruction, ADC in channel 1, AN1, and store the voltage on variable V1. This code that I'm presenting here, this is the main part of the code of how you read the voltage. In another code we will see the configuration of the PIC micro. So once you take a reading, an analog reading on AN1, and you store it on V1, now V1 is transferred to port C. Okay, because V1 is in binary code. So this code, bits 0 through 7, from the address L, which is the register that stores the low byte from the A to D converter. And so that variable, in this case, this RAM location, or this variable, is holds the value of the A to D converter, and it is transferring this binary reading into port C. If we are going to use 10 bits, then the address H, as we saw in the previous video, the analog to digital result high byte bit 0, which is in this case bit 8 for the A to D converter, will be transferred to port A, .4 or RA4, And bit 9, which is the most significant bit when you configure it for 10 bits, which is bit 9. In this case, RSH.1 will be transferred to RA5. We wait 10 milliseconds so that your eye can see the reading, and then we start clearing all ports, the 3 ports, and to be ready to take any reading. And here we have an unconditional loop or jump to repeat to keep reading at this speed. Of course, 10 milliseconds is too short. We can change it. And now what happens with the A to D converter is this: the bit 0 through bit 7. Bit 0 has a resolution for all the rest of the bits. So the resolution is given by 5 volts divided by 2 to the 8 minus 1, which is 19.60 millivolts. So this is the value. And because we have the binary weight in red, so the binary weight is 2 to the n. So we multiply the resolution, 19.60 millivolts, times 2. We get this, and times 4, okay, 19.60 times 8, and so on until you reach the last one, which is 2.48, 2.49. Here I'm rounding off the results. Okay, so in this way you can represent any voltage from 0 to 5 volts using 8 bits, okay, with a resolution of 19.60, or we can say 20 millivolts. Okay, that's the resolution. If you want to make it a 10 bits, so you will have to place here in the table bit 8, bit 9, and then you will have to do 5 volts divided by 2 to the 10 minus 1, and your result will be 4.88. Okay, I'm gonna put it here just that you don't forget that value. So 4.88 millivolts will be in case you want to work with 10 bits, and that will be the resolution, 4.88. In this case is 19.60 for 8 bits. Okay, so the code, let's start with the code right here. So first we declare in here the details about this design. We connect master clear RA3 or master clear to BDD internally. So we declare B1 as a variable byte. That's the first step. And then we define that RA0 and RA1, you see, I'm going to use those two as analogs. And analog input RA0, RA1 right here. And the rest will be digital. So all these 4 bits correspond to RA2, 3, 4, and 5 respectively. So, and they will be digital inputs, and these in yellow will be digital outputs. Now, because I want to read voltages on RA0 and RA1, I have to use ANSEL, analog selection channels. So wherever you have a 1, it'll be analog. So RA0 and RA1 will be AN0 and AN1, which will be analog inputs, and the rest will be digital outputs. Okay, we declare port C as an output with all zeros because all the 8 LEDs will be connected to port C. On ANSEL C is all zeros because it'll be a digital port. We don't want to use it as an analog. Trice B will be only has 4 bits, RB4 through RB7, and in this case they will be digital. Okay, the other ones in zeros, they're not implemented in this micro, and those will be digital inputs. We won't use them in this. We will not use them in this practice, but it is always a good choice to have them as inputs to protect the pins from short circuits. And with option reg .7 we control pull-up resistors, which we will not use. Then the ADFM bit, which we saw in the previous video, is a right justification for the A to D converter result. That's address L will store the least, the low byte, and address H the high byte, and they will be right justified. We disable the pull-up resistors, and we disable the analog, the comparator module inside. We don't need it. We declare OSCON 6.8 for to set the internal oscillator to 4 MHz. We don't want to change that frequency. We clear all port latches, and we clear disable. We rest assured that no resistors will be enabled, and we wait 1 millisecond, and right here we define the ADC bits. For the first part of the experiment it'll be 8 bits. Then we define the internal clock source, which will be clock number 3. It's an internal clock source for the ADC, the A to D converter. And we define the sample, the internal sample from the A to D converter, sample and hold, that'll be 50 microseconds. And that allows you to the voltage to change, and it will not affect the conversion. Port A, so we clear all ports, then we clear the register the A to D results, low byte and high byte. And here is the heart of this code. Let me amplify a little bit. Okay, so right here we create a label called RPT, and we start taking a reading, ADC in, take a new reading, a voltage reading, and on channel AN1, and store it on variable V1. Okay, it'll be stored there. So variable V1, transfer this variable, this is the source, this is the destination, transfer V1 to port C. So we will see the 8-bit conversion on port C. We're not using the greens, these ones that I have in green. That's why I'm placing here the semicolon. And so we have 8 bits transferred for 250 milliseconds. We will see them on port C. Then we clear the 3 ports. We clear variable V1 to make sure it doesn't contain any other data. And then we clear address L and address H, the A to D results from the A to D converter, to make sure there's no data there. And we go back to RPT. Notice that this happens in 1 microsecond, 2, 3, 4, 5, and 6, in 6 microseconds, and then 7 microseconds to go and take another reading. So these microseconds are there, but are really not affecting our process. But the important thing here is that once we transfer port C, it'll stay on port C for 250 milliseconds. Because this is a quarter of a second, it allows me to take 4 readings per second, okay, which is good for our eyes, so we won't see the LEDs blinking or flashing. We will see a steady reading. And of course you can start changing the voltage with the trim pot, and you will see how the binary code starts changing. So I recommend that you move the voltage all the way down to 0. The least significant bit, the LED will be flashing. Let me show you here in this one. So the least significant bit, which is RC0, will be flashing. So with 0, 1, 0, 1, that's normal, because that's the error that the A to D converter has, plus minus 1 LSB, or least significant bit. And so this, if you want to have a 10-bit analog to digital conversion with better resolution, equal to 4.88 or let's say 5 millivolts resolution, you have to first here, you have to set it to 10, this number. You have to set it to 10 bits, and then you have to remove the semicolon here, and this will, when you do the code, this will become black or blue. So that'll be indicating, let me finish here, that'll be indicating that now you want to see from the analog to digital result register bit 0 and bit 1, you want to see them on port A.4 and port A.5. So you will see the 10 bits for 250 milliseconds. Okay, and we follow the same process. So that'll be the change you will have to make to have a 10-bit A to D conversion using the 10 LEDs that we just saw in the experiment in figure 1. And of course, when we transfer here address H, address 1, sometimes, of course, we know here the voltage is stored in variable 1, but sometimes you might you might don't want to see it as or do the transfer from variable V1. You can transfer directly address L. Okay, so transfer the low byte from the A to D result to port C. Okay, that's another way to do this experiment, especially when you're doing it at 10 bits, because you see here is the low byte transfer to port C, and the 2 bits from the high byte to port A.4 and port A.5. Okay, so this is a way to do 2 types of conversions, and the circuit will be like this. This is where you see how when you are increasing the voltage, you can see here, you will see binary code. So you see all these 3 bits equal to 1 and the rest 0, so you have 6 ones. What voltage is this represented in binary code? So you have to add this voltage, these 6 bits from bit 5 through bit 0, 627 millivolts plus 300, it will be around 940. And with this one, you have 1000, 1076, and 1080, 1100. So you can say 1100 millivolts or 1.1 volts. That's what it is representing in the picture. So you have to add them. Okay, but you will see binary code. Of course, there are stages, binary codes, where all of them will be ones. So if all these bits are equal to 1 and you're working with 8 bits, that's 5 volts. If you see that bit 7 is on and the rest is off, that'll be 2.5 volts, as you can see here. If this bit is equal to 1, it will be 1.25 volts. Okay, in the previous case, you saw all these bits on, we can say in green, you saw all this on. But what is the next stage binary in binary code? If you have all ones here, then all of them will be zeros and this one will be 1. So I was telling you 1.20 or 1.25 volts, and that's correct, because that's the voltage we can see here. So, and another thing, another detail, so that will be the circuit to test. And let me go to page 50. If you're interested, one of the next designs, let me reach page 50. Yeah, page 50 is right here. So in this design, you can see an A to D converter. Let me decrease. Okay, right there. You will see this A to D or voltmeter, where the A to D converter in this PIC Micro is also working at 8 bits, but you can use some instructions to convert the binary code into BCD code and separate each digit so that you can have here the maximum voltage 4.99, and those voltages will be transferred in BCD code in parallel to this decoder. So every decoder will drive the liquid crystal display. Okay, so that you can see a standard reading and voltage reading. The decimal points are not used, and the common, they have to be connected to a frequency, a low frequency, 250 hertz, connected to the phase, so that you can drive the liquid crystal displays. And that'll be another lesson where I will be explaining those details. And this is how the circuit is made. Okay, so you can see here how you can transfer data using decoders to from the microcontroller. Okay, so that's all for today, and thank you.